all that said before YouTube started recording, so it's fine. Yeah. Although most people would likely agree with me, experts in the field. Probably. That's the fun thing about the internet, though, too, is that you can find evidence to back up any opinion that you have. Yeah. Let's, let's with the sound. I don't know who. Oh, there you go. I'm very upset that somebody. I'm gonna trip over this thing. About that. We'll find out. Aaron, you got time after class to talk about that problem? All right, cool. Stick around. Give it. All right, it's 11 o'clock. Let's get going. All right. Let's start off. Lord, thank you so much for everything that you do for us and all the blessings that you bestowed upon us. Pray that you would continue to help us through this semester. Help us to stay focused on what we need to do and to get all the things done that we need to. Also, help us to set aside a little bit of time for ourselves to rest and make sure that our minds are not getting overloaded. In your name we pray. Amen. Rest is important, guys. Rest is important. I once had a professor in my undergrad who told me, he overheard me saying I was up until 4 in the morning doing a paper for a non-engineering class because reasons. Probably because I waited until the last minute to start it because it's not an engineering class. So clearly I could wait till the last minute. It's easier, right? Not necessarily true. But he overheard me saying I should have just stayed up instead of going to sleep because I only got like 2 hours of sleep. And he's like, nope, disagree. Any sleep that you get is definitely worth it. You need your body to reset. And it's very true, right? So make sure that you guys are having some self-care, right? Treat yourselves okay. All work will burn you out. So, all right. Anyway, we're gonna recap. We got a lot of things on here. It looks like a lot of things. I would say it's a medium amount of things. A lot of these are like one slide and then we go to the next topic. It's not like multiple slides per. Okay. See, moments. Yeah, sure. And couples. All right, so if a system, a beam, whatever we're investigating, if that is under some set of forces, right? And let's say for a particle, right, when we were talking about particles, moments don't really exist, right? Because everything, it's a particle, so it's infinitesimally small. And so everything passes through the center of that particle, so it doesn't rotate. Right now, some of you who are super into quantum mechanics will say, but that's not true because I know that there's upspin and downspin, quarks, and please see my comments about atoms from a previous class. No, all right, quantum mechanics is a different thing, and the Newtonian physics don't apply there. Okay, we were talking about Newtonian physics, all the stuff that Isaac Newton invented to torture you specifically. Okay. Great. So we're going to say that a particle is infinitesimally small, and because of that, if I push on a particle, there's no spin that's getting imparted to that particle, right? So there's no moments, there's no rotation. But once we have a collection of particles that move together, i.e. a rigid body, then when I start pushing on things, if I push away from the center of this, it rotates, right? It's not a pure rotation, it translated a little bit, right? But it rotates nonetheless. And that is due to a moment, right? So a moment is a force that is some distance away from the point of rotation, right? So when we have a force that is not going through a point that we are interested in investigating, it creates a moment. And the larger the distance, the larger the moment. And we talked about this with the wheel, right? With the valve wheel, right? The further away I put my hands, I can use the same force but get better rotation because I'm magnifying the effect of that moment. Right? So what happens with a couple, right? And why is that useful? So if I have two forces that are acting on a rigid body and I know the distance between them, I can determine what sort of rotation those would impart to that object, right? And so I can take those two forces and I can say, you know what, the net effect of this set of forces is a rotation. And it's called a couple because they're two, right? And so if I position this couple, I can actually remove that couple and just talk about a moment acting on my system. And that's the whole idea behind couples, is that we can find these sets of forces and we can take them off of the FBD and replace them with a single moment, right? And so instead of having multiple things that we need to be aware of, we're just worrying about the net effect, okay? Now, for moments, this is a little bit abstract, and we haven't really shown why you would want to do that or why it's useful, right? And we will get into a little bit of that later today. But we'll get into some other ways to simplify systems that are used quite a bit more frequently, okay? When you take a force couple and turn it into a moment, that becomes a free vector. So you can put it wherever you like on that body, right? Lunch. I don't have that problem making my lunch in the morning. I know exactly what it's going to be. But respect, if you guys don't just fall into the Chick-fil-A trap. I don't even know what's open here on campus over the summer, but yeah, sure. President Mueller likes to tell us all the time that we have got like 500 Chick-fil-A locations on campus, so it's great. 3 moments. It's probably 3D moments. Okay, 3D moments are kind of weird to conceptualize, and they're not intuitive, right? And I will fight anybody who says so. Okay, I will. So they are not intuitive, so you can't really just look at it and say, okay, well, this is going to cause a moment in this direction and that direction. In 2 dimensions, sure, right? Like you'll see me use this guy, but if I push here, okay, that clearly is going to cause a rotation in one way or the other, right? But in 3D, once I start pushing on things in 3 dimensions, each component of that is going to cause a rotation around whatever axis that it has. And it's sometimes tricky to determine by doing it with the scalars, right? So I would urge you to just trust your vectors, trust your bookkeeping, and trust your math, right? If you are bookkeeping your vectors correctly and you do the cross product, everything else falls out and you don't have to really worry about which way does it go. Right? That kind of goes into direction, right? The direction of moments. Right hand rule, always the right hand rule, right? So counterclockwise is positive. Again, we've said it, I've told you this last class. The book sometimes will define a different thing. Like you'll see, okay, well, if we assume that the moment is positive clockwise, I will never do that. I will always use counterclockwise as being positive because that is the correct way to do it. Okay. Sure, you can define whatever coordinate system you want, right? You can, and that's perfectly fine. And as long as you're consistent, that should work. But one of the things that you're going to start seeing is that once we start solving for forces and moments, we're going to not just rely on whether it's positive or negative. We are also going to start assigning directionality to them when we write down our answers, because there are certain times when you might choose a force going in one direction and I might choose it in another, and one of us gets a negative sign. That doesn't mean that what you did was wrong. It just means that you created an unknown in the wrong direction. So you got to flip your sense, right? We'll talk more about that later, actually. Product. Projection. Projections are tricky. The best example I can give you is that problem last time I thought was pretty easy to see it. I forget which, there was one of the first ones we did. Projections are all about triangles. It's all about trig. So how much trig do you need to do to get it to the axis that you want, right? So if you have a force vector in 3 dimensions, chances are that if you rotate it into either the xy, xz, or yz planes, you'll be able to get some information directly from a single trig identity, right? Then what's left can probably be broken down into the other 2 directions, right? And that's why we have the sine. One of them will be, in the last problem we did, we had like the sine of the angle was the z direction component. And then that left us with something that was sitting on the xy plane. And so you can take that vector as the new hypotenuse and break it down into x and y components, right? So now it's the sine of something or the cosine of something times the sine or cosine of a different angle, right? Cross product. I mean, cross products are they're everywhere. You're not going to get away from them. There's a lot of things that turns out in the real world that work like that. Magnetic fields are one of them, right? So you got to take the cross product of the voltage and something else I'm forgetting. I'm not an electrical engineer, so I don't need to memorize that. It's fine. Anyway. Any other questions, comments, concerns about last class that I didn't cover? I know the balloon question was still up there. Go back. I would say if the balloon question is still nagging at you, I would ask you to go try it on your own and come talk to me about it. Okay? And then we can get it squared about what is actually kind of what's the root here that's kind of causing the issue. All right, last class we ended here. I told you we'd start here. I kind of gave you insight into how we were going to try to go after this problem. But what were we given? Well, we're given this drawing. We've got this frame. I know it says that it's a beam. It's not a beam, it's a frame. What's the difference? We'll get to the difference. You don't need to know the difference right now. We'll talk about difference between a frame and a truss and a beam later. We have 2 couples that act on this. I think that should be pretty clear that we have 2 couples because we have 2 forces that that are equal in magnitude but have opposite directions, and there is some distance between them, right? And so we can clearly see that we have 2 couples here. We know that the distance d is 4 feet because this picture was taken from the textbook, and there's probably a whole slew of problems in there where they change what d is, or at some point they ask you to find what d is, right? So that's super fun. What we are asked to do is find the resultant couple, okay? Great. Well, that's weird because up until this point, we only ever found we had 1 couple, and then remember when they say the couple, they're asking you for the moment specifically, right? We're looking for the moment, the resultant moment. The resultant moment. Okay. So let's start with our free body diagram to kind of get that rolling. So I'm gonna cheat and I'm gonna use these tools to help me make my frame here. That's true. Use your tools, not cheating. Nobody said I couldn't use these zoom tools. That one's not gonna work, huh? Okay, that's fine. Good enough. So we've got a point here. We've got a point here, one about here. Okay. And I'm gonna put a point there. All right, well, let's start drawing some forces. I'm gonna start with my couple that's up here. There we go. There. So pretty good. What are those? Those are my 50-pound forces. This is 50 pounds. We are given this angle here as 30 degrees. I know that that's not clear to see, but you'll see it on this one maybe. 30 degrees, right? So we're given this couple here. We're given some distances that we'll write in a second, but let's get the other couple drawn on there as well. Okay, and so that one's going to be like here and here. What we were told about these specifically was that they are 3, 4, 5 triangles, right? Great. So we got all that, and we'll put in our distances now. So we were told that from the base here up to our first force, that's 3 feet. We know that this distance here, from here to here, was given as 4 feet. Right. Then from this point over to there is 2 feet. And here to here was 3 feet. Okay. And that should be to the point. Anyway, we'll discuss whether or not this is drawn to scale in a minute. Let's start here. Newsflash, it's not. Okay. So if we go back just really quick and look, you can kind of see where we're at. This is 1 foot between point B and the top of that force, which is one that I forgot. So we'll go from here to here, 1 foot. Okay, I think we've got all of our things in there. I'm going to adjust this just slightly because it's bugging me. It goes to the point of application, and this goes from there to there. Nope. No, we're just going to leave it. It's fine. There we go. Perfect. It's perfect now. Yep. For what, the diagonal? No, it does not. We are going to assume, well, not assume, we are told that our X and Y coordinates are there, right? So we're doing a positive XY like this with rotations in that direction. Okay? Free body diagram. What do we know? We know distances and forces, right? So we'll write it down. We'll say, just for completeness, what is known, distances and forces, or dimensions and forces. However, you know, we're given this original drawing, right? And we created a free body diagram. What are we asked to find? The resultant couple, which I'm going to call M sub R for resultant moment. And that's what we're looking at. Okay. So we talked about this a little bit last class, there's actually two ways that you can kind of go after this, right? You can find the vector between the two forces, right? The R vector between the two forces, and then do R cross F to get your moments, and then find your resultant, right? You can do that, and that's totally fine, okay? Why am I hesitant to do it that way? Mainly because that doesn't help me get the resultant. That helps me get two different moments that have different coordinate systems that I'm going to have to break down into X and Y components anyway to get the resultant moment, right? Because remember, the moment's a vector, so I'm going to have to, it's going to be a little bit messy. But you can do it that way, and that's totally fine. What I'm going to do is I'm going to do the trig up front. I'm going to break all of my forces down into X and Y components first. Then I'm going to find the moment due to each of those, and then I'll find the resultant. 6 of one, half dozen of the other. You should get the same result. One is just a little bit more trig heavy with the, it's just carrying those. Do you want to do the trig on the known quantity of the forces, or do you want to have to do trig to figure out how a 3, 4, 5 triangle, then basically rotating my coordinate axis to figure out what the distances are between those two things, and then have to do a third coordinate transformation to bring everything back together again? It's not impossible. It's just tedious. And I would argue, I think I said this last class, I don't really want to make you guys' lives harder. Like, life's hard enough. Let's do this as the easy way, right? So anyway, we're going to do that. We're going to start with our 50-pound force vector. I realized I didn't write down what the other one was. Let's put that down on there. That'd be a good idea. That's 80 pounds. These guys are 80 pounds. All right, so if we're going to start here, I will start with the 50-pound vector, right, which I'm going to call F1. F1 is 50 pounds, right? And if I want the X component of that, right, remember this is the magnitude of the X component. I haven't really picked which, one's going to be positive, one's going to be negative, right? So if we're just looking at the overall absolute value of the X component, right, what's it going to be? Well, it should be 50 times the sine of 30 degrees based off of the angle that we have, which I will just simplify to 25 pounds right now, because I know that we use sine 30 so often that I know that it's 1/2 off the top of my head. Right, and that's one of those ones that you just kind of, we're talking about memorizing before class. That's one of those things that happens so often, you just kind of hope that you get a sine 30 or cosine 60, which is the same thing. All right, so then how do we get the y direction? Well, use the cosine. Right, and if you do that math out, 43.3 pounds. And remember, these are magnitudes. I have not assigned direction to them. We are going to do that manually later once we calculate the moments. But, all right, anyway, let's do the F2 is our 80-pound force, right? So 80-pound magnitude. If I want to break it down and get the magnitude in the X direction, right? Well, that would be 4/5 of 80, right? Which is 64 pounds. And in the y direction would be 3/5 of 80, which is 48 pounds. It's like they gave us these nice numbers on purpose, right? Super nice. No weird decimals. Well, 0.3, I mean, 0.3 is not that weird, right? It's all right. Cosine 30 is not great. The rest of it's fine. The rest of it's fine. Yeah. Yeah, no, it's Hibbler. You got to talk to Hibbler. I think he's alive still. I don't know. We talked to a representative of Hibbler, the estate of Hibbler. Anyway, cool. So we have this. Now what do we do? Well, all right. if you were to break these down, right, how does this affect what our free body diagram looks like? Well, it affects how it looks by, I'm just going to change how we drew these real quick. You don't have to redraw them if you don't want. I think it can be helpful, right? So, oh, let's try that again, but with the right color. So we had one that was up and to the right, one that was down the left. Is that there? Nope. This one goes up. I'll move it in a second. Okay. Once again, not drawn to scale, but just to show you guys what we've done, right? So by doing all that, we've broken our forces down into their X and Y components. Not crazy. It would have looked really cluttered if I kept all of the force vectors on there, right? But what's interesting about this, right? All right, well, let's start off by finding the moment due to the 50-pound force, right? The 50-pound couple, okay? If we want the moment due to the 50-pound couple, doing this allows us to do some really interesting cancellations, right? So the moment due to the 50-pound couple, right, is equal to what? Well, it's a couple, and so it's in 2D, so I don't really need to do the cross product. So first thing I'm going to do is I'm going to look at this. I'm going to say, all right, well, what is the perpendicular distance between these two forces from here to here in the y direction? What is it? It's 3 feet, right? And in the y direction, we said what? We had 43.3 pounds. In the y direction, we've got 3 feet, right? Okay, we'll talk about positive or negative in a second, right? What about the x component? What's the perpendicular distance in the x direction? It's 0. They pass through each other. There's no moment due to those for this couple, which is yet another reason why breaking it down into x and y components made it really nice, because then we don't even have to deal with part of this, right? So based on this, the y direction forces are the only thing contributing a moment from the 50-pound force. So is that a positive or a negative moment if I'm going to push up and down on that beam? Yep, negative, right? It goes clockwise. So we will just go ahead and say that this is a negative 129.9 pound foot, or foot pound, or however you want to call it. Okay, great. Now we got to do the same thing for the 80-pound force, right? So let's calculate the moment due to the 80-pound. And technically this is a vector, right? What we've just done. Because this is 2 dimensions, this is in the K, right? I just didn't write that originally. I glossed over it and I apologize. I shouldn't have. I've dishonored my ancestors, all that stuff. Okay, great. Okay, remember, we assigned, once we determined what direction it's moving in, we know what axis this is rotating about. This is a 2-dimensional problem. It makes it very easy for us to understand that this has to, if this was left unchecked and it was free to float in space, that would just start spinning in around the z-axis, right? It just start spinning, assuming that those forces aren't offset in the z direction, which we have no reason to believe that they are. Anyway, great and good. Next, rinse and repeat for the 80, right? Okay, so this time, this is drawn really, really poorly at this, for this right here, but I'm gonna move this maybe. I'll move that there. Nope. That's what you get. That's what you get. We'll move that there because that's where that should be, really. Okay. So y direction. Let's start in the y direction. What's the perpendicular distance in the y direction between these two forces? The orange ones. It's 0. Same reason as before. They pass through each other. No moment. But the other one is 4 feet away. And we know that because we were told that D is 4 feet away, right? And so there we go. We'll have 80 times 4. Okay. That should be, the last time I checked, well, sorry, not 80, 64. Ugh. Oh boy. Like I said, 64 times 4, which should give us 256 foot-pounds or pound-feet. Is that positive or negative, that rotation? So I've got my thing. I'm going to pull like this. Is this positive or negative? I guess for you guys it'd be this direction. Right? Yeah, it's positive. This one's positive. We'll call it out in the K. We've got our, hey, look at that. We've got 2 moments in the K direction. We need the resultant moment. What's the best way to find the resultant moment? You should just add them. Percent. Okay, great. So the resultant moment is 256 minus 129, which comes out to like 126, 127. Right. And I'm going to switch this one and call it foot-pounds because reasons. And there you go. And where do we put this? It doesn't matter. It's a free vector. Here is my moment. There you go. Boom. MR. Vector. Right? Okay. Why is that important? Well, we haven't said why it's important for us to be able to understand what the moments are. Well, I kind of did, right? So again, this is statics. So if these applied forces create this moment on this frame, right? Why is it important that I know that? It's important. Whoa, man, I'm gonna die here today. Look, that was scary. I was a little scared there. Whew. All right, regrouped. Why is this important? Because of that. Okay, because I created a moment on that chair and it was not statically prepared to handle that moment. Okay. In this case, if the base cannot handle that moment, it will rip out of the ground. Presumably, this structure is meant to do something and not just be aesthetic, right? Presumably. Okay. All right. Anyway. Whew. That's what, whoever moved that table really did that. That's their fault. I did not. I came in here and it was over there. And I'm going to file a complaint. I'm going to find out who else teaches in here. All right. Any questions about that one? Any questions? Yeah. Isaac. All right. Good question. So why is the resultant in the K direction? So if I have these two forces, we're simply in the XY plane, right? Everything that takes place here in the XY plane. So anytime when these two, if I have two forces that are equally and oppositely applied, that's going to call, if this was allowed to just freely float, right? And I was to push it, it's going to turn around the z-axis, right? So when we have a moment vector, when we call out k, we're not saying that it's in the k direction, we're saying that it's about the k direction. So it's spinning around the z, right? And for two-dimensional cases, whenever we have rotation, it's going to be an out-of-plane rotation. You can't affect a moment in, how do I say this? You can't affect a moment about a plane if all of your forces are in that plane. It mathematically can't happen, right? In this case, I can't cause a force in the x direction and in the y direction cannot create a moment around the x or y axes. Only a force in the z direction can cause rotation around the X or Y axes, right? And if we're just, so let's keep that in mind. Whenever we're doing two-dimensional problems, it simplifies it quite a bit. Yeah, Colin, so. Right. So remember when we're dealing with couples, what's the idea with couples is that we need to know the distance to the distance between the two vectors that we're making a couple, right? And because those have the same line of action, the distance between them is zero. Because remember, you can move a force anywhere along its line of action and still have the same effect of that force, right? Like the truck pushing the thing that we talked about last class. Yep. Cool. Any other questions? These are good. No. All right. Cool. All right. So let's see. This one's for you guys. A couple is applied to the beam as shown. Its moment equals what? So this is a very polite way of me asking you to find, I'm not giving you multiple choice. You need to do the calculation. All right. So find the moment, the couple for this force. I will give you a hint because you're asked that it's a couple, they're equal and opposite. So one, they should both be 50 newtons and 345. All right. Then you're going to put it on the whiteboard when you have your answer. All right. When you got it, when you got your answer, throw it on your whiteboard. Whiteboard up proudly to display. Make sure no one else can see it. No. Okay, okay. Another minute, then we gotta throw up an answer. Yep. Chapter 5, that's a good question. Depends. Probably next week. Okay, what we got? Throw them up. All right. No, there's no answer, guys. There's no answer. Oh, there was choices. Awesome. What is it? So you guys all calculated it anyway. So 50, 60, 80, or 100. Most people had 60. The answer is 60. Why? But why? Because I told you. Yes. Because that's what your math said. Because of the same reasons last time, right? When you saw this, you said, hey, in the last problem, Dr. D made a really big deal about how the two forces that point toward each other don't participate in the moment calculation. And so you just calculated what the y direction one was and the distance between them, and you multiply, and then you figured, hey, if I had this beam and I was to twist it in that way, I would get a positive moment, right? Great, perfect. Okay, what about this one? Can you determine the couple moment m is equal to r cross f if, well, you don't have to, all right, so this is what it's asking you for is the r vector, okay? It wants the r vector if f is negative 20 in the k, right? So you want the couple moment of these. But you're not calculating the moment, you're figuring out what r is. What is the r vector? I'll give you choices on this one. Which one of these is your vector? A good question. Oh, it's over there. It's over there somewhere. Oh, there, there. What do you guys think? A, B, C, or D on this one? Let's go. Okay. D, C's. Okay. C, C, C. We got, throw them up. D's and B's. Lots of D's, lots of B's, couple C's. Oh, all right. All right. Well, I'm going to tell you right now, it's not A or C. And that's because point C isn't even on this diagram. Okay. That's number one. Number two, it has to be either B or D. What are we looking for, right? We are looking for the distance between these two vectors. Which one are we going to pick if we said that f is negative 20k? Right? Where are we going from? We want the one that terminates where? On the negative, right? So we want BA, it's D. Right? We want the one that terminates on the force that we're using because that's the distance to that force from the other force. Okay? But you can also say, well, RAB would be fine too if you used the positive version of it, right? So just be aware of you want the force that points to the one that you're using, right? You want the distance the vector that points to the force that you use to do the calculation. That's what you want. Yeah. So you got to use the 150 and the 200 and then 200 over. You got to do all sorts of SolidWorks math, dimensioning. It's a dimensioning problem. All right, here's the things. You got homework due tonight. Water tower project plan on Sunday. Quiz a week from today. Quest. We're calling them quests. It's not like it's like a quiz plus a test together. Homework 3, homework 4, right? And then quiz 2. Quiz 2 will be on homeworks 3 and 4. There you go. Okay. Questions on the things that are due? Nope. All right. Here's the Dr. Deism for today. Work hard up front so you can be lazy later. Okay. This is something my PhD advisor told me back when I started my PhD research. You want to do as much work up front in case things like, and this is, I think this is what I tell my capstone groups too, over prepare in the beginning. That way at the end, when you don't want to do anything, when you're worried about graduating and all you want to do is just get through your classes and work hard on the front half. And then in the back half, you can let your foot up off the gas a little bit. I'm not recommending all of the bit, just a little bit. Okay. Does that make it makes sense, right? Work hard up front so you have some room to take some time on the back half, right? Simplification of force systems. That sounds interesting. It is. You're right. I mean, that is also it's a rude question. Okay, and I don't appreciate that. But there is a method to our madness of what we're trying to do. We're trying to build the foundation still. And this, you have to think about this, right? If you were taking this in the regular semester over 15 weeks, right? This we're already like 4 weeks in, right? In our 2 weeks. And so people that take this in the 15 weeks, they're for 4 weeks, they're just looking at cross products and how to move moments and stuff around, right? We're doing great. All right, so back to our puddles of water or blue potatoes or whatever we're calling them. So, all right, I have a bunch of forces acting on a thing, right? And that seems really complicated. I would rather have one force and one moment. Cool, that seems much more manageable for me to work with. So when I have a number of forces and a couple moment, so this is again, this is why being able to identify couples is nice, because then you can reduce it to a moment and you might have a resultant and a moment, right? So we can make two force and couple system that are equivalent systems. Remember, because they are equivalent because it is the same net external effect on what we are looking at, right? If we don't, we can regroup forces and our moments in whatever way we want, as long as we don't change the net effect of having those forces on there, right? Cool. So moving a force from A to B when both points are on the vector's line of action doesn't change the external effect, right? We talked about this last class. This is totally allowed. You can move this force to the end of the meter stick, right? Or you can move it to where the hand of the person is, right? Doesn't matter as long as you don't change the sense of the vector, meaning its directionality, right? We can slide the vector along. Okay. When a force is moved but not along its line of action, that's an external effect that you have added here, right? If I move this vector somewhere not along, let's say to the very top instead of the center of that meter stick, right? Well, what happened? Well, now I have to do some more work, as I can do that, but I have to take care of the net effect that I've created, which means I have to add in a moment that will counteract the net effect of moving the force. Okay. That is a free vector moment because you've essentially created you had to create a couple to take care of that, right? So in this case, it's weird, but we'll show some other examples, right? So we have several forces and several couples, right? We can move them to a common point. So let's say it makes sense for us, like I've got all these things acting here, right? Like in the top, but I would rather consolidate them all to be at point O, because point O makes sense to me. I'm able to put my instrumentation at point O, right? Maybe there's some reason why point O makes sense for me to move this here, right? Maybe I want to move all of my forces to the hinge on the door, right? Great. In order to do that, I need to create a bunch of moment couple systems that I can then consolidate into resultants, right? So notice we had a moment applied down here and our forces, right? This generates two new moments when we move these things, because these aren't along our line of action, right? And so by me moving the force, I've created an unintended moment that I need to counteract. Okay. How do we do all this? No, that's just telling us how to find the resultants, right? And that's fine. We know how to do that. So if we're talking about a two-dimensional system, 2D, we've got these things, they lie in the XY plane. We reduce their equivalent system. We can obtain that using the following three scalar equations, right? So you can use, in 2D, we can use these equations, right? Where MC is specifically any couple moment, right, that we produce, and MO is the moment about point O. Okay. So you can kind of see it here. It's kind of difficult. I'll try to highlight it really quick on the slide. Okay. So what they're showing here is my resultant weight I've moved to point O. And here's my resultant moment. Okay. So how do we do that? First, we need to create a resultant weight, right? WR. Both of these act in the Y direction, so we're just going to add them. You just add the weights, right? That's fine, but when I move that weight to point O, I have then created a moment that wasn't already there. And so to balance that, this new moment exists, which is just the sum of the moments. Say I moved weight 1. So weight 1 creates a moment at O, weight 2 creates a moment at O, and then I slide the moment to point O, and now I have my weight acting at point O. Okay. It's a lot less, it sounds complicated when we talk about it, but in practice, it's pretty straightforward, right? You add your forces, and then you find the moments due to those forces at point O, and then you've consolidated everything that you need. Okay. In 3D, this is kind of, it gets messy. Okay, as is typical for adding the third dimension, right? So if FR and MRO are perpendicular to each other, then the system can be further reduced to a single force FR by simply moving FR from O to P. Okay, so if we have something that's concurrent, coplanar, and parallel, then we can always reduce it to a single force. Okay, so coplanar meaning they exist in the same plane. Concurrent meaning that they are in, parallel means that they are parallel to one another. Concurrent meaning that they are happening at the same time, right? So then we can move everything to just one spot. But look what happens. You can see it here, right? Highlight it with the mouse, right? Look, this is the new force resultant. I took all three of these. These are concurrent and coplanar and parallel, right? They all exist in what we're calling the XY plane, right? Or the AB plane, whatever you want to call it, right? If I move these all to point O, that's great, right? But that creates a moment, right? So I can add them all together, put the resultant here, and that's a moment, right? But in this case, I can also say, well, in order for me to produce this moment, I would have to move this force vector a distance of d away from point O. And this creates the same moment as that. So now I can reduce it by getting rid of the moment. Does that make sense? You're doing the moment backwards, essentially. You're doing the moment backwards. In order to solve for d, you have to know what the moment is and then figure out what distance away this force, FR, can create this moment if we position it correctly, right? Again, we're dealing with net effects. If the net effect is that there's some moment about that axis, I can say, well, if this is 7 pounds and this is 7 pounds. If I put this 1 foot away, this force has also generated that moment. Does that make sense? Okay. It's confusing for sure, right? Why is all this helpful? Well, it's helpful because I can take a whole system of three forces, condense it down to one, move it to where I need it to be, call it a day, right? Really helpful when we start talking about distributed loads in a little while. But let's try one here. Let's try one. So what do we have? We have this geometry and this 2D force system. It was nice that they told us it was 2D, but you would have assumed that other anyway by looking at it, I hope. So what do we have? Well, first thing we'll do is we'll draw our free body diagram, right? I'm going to draw really, there we go, perfect. There we go, that's point A. We'll say that we have some force here that's 200 pounds. And then I'm going to have my couple, and that's a 345 right here. And then this guy, hold on. This guy's 50 pounds. And that's 30 degrees off the vertical. So as a matter of discussing notation, if you didn't have this line here, oh, if you didn't have the curve showing you that it was an angle, right? And I just wrote 30 degrees, like right in there. Oh, come on, you can do it. And I just wrote 30 degrees right here. That is telling you that the angle between the hypotenuse and the vertical is 30 degrees. Yes? Would you guys see that without the aid of connecting the two lines, right? So if you're not given like the arrows saying that this is the angle, but it's put like right in that corner, then you should assume that that is the angle for that corner, right? Okay. Good. Great and good. What do we know? Well, um, let's we know our forces in our geometry. Yeah, spelled it right, maybe. We got to put our distances in, right? 3 feet. This is pretty nice. It's like 3 feet to everything. It's great. And we'll do our coordinates in this way. Okay, cool. So what were we asked to find? The equivalent resultant force and couple moment acting at A, and then the equivalent single force location measured from A. Okay, so there's three things that we're asked for here, right? We want the resultant force, we want the resultant couple, and then we want to know if I just simplify this into a single force, where would I put it, right? Where would I put it? So we're going to say we want FR, part A. For part B, we want MR. And for part C, we're looking for the distance. We'll call it D sub A. That is what the problem is asking us for. And I would say that based on the things that we have, we should be able to do those things, right? So let's do that. Let's do that here. So the first thing we want to see is we want to try to figure out what FR is, right? And you can see our drawing up there shows that FR is somewhere over there, right? Sure, right? When we combine all of these, we're going to end up having some new force vector, and the distance that it is along the beam is going to be affected by how large each of the components that we have is. Since the 200 pounds is the largest component, you're probably going to skew towards the 200 pounds, right? But let's do the math out and see what happens. First thing, let's break down our forces and find the force resultant, right? Because part A was to find F sub R. So if I'm going to find F sub R, well, I need to know all the X and Y components of all my forces, right? Let's do the easy one first. We'll call it F3 is 200 J pounds. That one seemed pretty good. Right. Okay. You could also call that F3Y, or you could call it whatever you want. I like to have a variable name for it because if I just write 200 in the J, I can't track it, right? So I just create a variable name for it. Let's do F2. The brown one, or the dark red one, is what I'm going to call F2. And if I want the X direction component of F2, what do I need to do? 3/5 of 100, which is going to give us 60 pounds. This will be in the I direction. Even though I know we call it F2X, right? So you don't need the I to call it out in the I, but just as a reminder, I'll remove it though. Let's get the Y direction component. Sure thing. F2Y. It's negative 80. Pointed downward, right? Pointed downward. And moving over to the 50, right? We can do F1 in the X direction. Should be 50 times the sine of 30, which is 25. And we did 50 cosine 30 earlier, and we found out that that was 43.3. That one's pointed up, so it's going to be positive. F3 has no X component, right? We could write X and Y components. I think we would, at this point, we don't need to. I don't think that that's a value add any longer, but we see that it's 200J, so that's fine. Great, so if we want the resultant, what do we do? Well, we add the X and Y components and we do that. So let's do that. So it's the magnitude. So for this resultant vector, if the X components are 60 and 25, that should be 85I. And then they're going to be 200 minus 80 plus 43.3. So 243.3 minus 80, 163.3 by J pounds. So we have our Cartesian. Is that good enough for this particular, is that good for this in particular? Yeah, sure, that's fine. Doesn't specify whether it wants magnitude and direction in terms of an angle, right? You can get it very easily from this. This would be an acceptable answer for a quiz unless you were told to write it in a different format, right? If you wanted to, right, you could find the magnitude. You would take the Pythagorean theorem, 85 squared plus 163.3 squared square root, and you'd get 184.1 pounds, right? So just for completeness, I will write down, right? Not that it was asked for, but to complete it in everyone's minds. You can also report this as a magnitude of this and an angle of, sorry, tan inverse goes first. And an angle of 62.5 degrees. Ooh, great. So, hey, go back up to that picture with the blue arrow. That's definitely not drawn to scale. That looks like 45 degrees. It should be tilted more towards the 90, right? Should be, it'll have a little bit more vertical. Yeah. It'll have a little bit more vertical. We wouldn't expect it to be purely vertical because there are X components from the other two. So it's going to pull that vector down a little bit, about 30 degrees. Right. Okay, great. So we did that. And we have FR. So now we need to find the moment, the resultant moment. Okay. How are we going to do that? Well, we've got everything that we need to do that. I'm going to take this result here, this FR. I'm going to move it up here so that we have it. I'll even take these guys. You know what? No. I'll delete them. I'm going to leave my forces up here for a second. Well, more than a second. I'm just going to leave them here. So we're going to do part B now. Find the moment resultant. Why would you leave those? Specifically, it asks for the moment about point A. So let's call this MRA, right? Double subscript. Just to remind ourselves that we're going from point A. If I want the moment about point A, I need to look at all of these forces and find the moment about point A. Okay. First one, let's go with the 200 pounds, right? So moment about point A. If I have a 200-pound pushing upward from point A, all right, hold it there, positive or negative? So we should have 200 times 3 feet. Okay, so far so good. All right, what about the 100 pounds that's down at an angle? What do we do with that? Well, we have the components. All right, the x direction component passes through point A. No moment. So we just need the y component. All right, that is negative 80. So that's down from point A. Is that positive or negative? And this time you ignore the negative sign on the force because we are assigning it. Remember, we are doing the scalar portion of it, right? So we are assigning our directionality as we go. No. Okay, we're assigning the directionality as we go. Okay, and then the last one. What about the 50-pound force? Which components do we need? Do we need both of them? Just the y again. Oh, and that one's pointed up. So since we didn't move where A was, since it's not on, if it was on the opposite side of A, right, that would change the sense of the rotation, but it's not. So this is going to be plus 20, oh, sorry, 43. Looking at the wrong one. Plus 43.3 times 9. Right? And obviously, when we put that all together without needing a calculator, it's 509.7 foot-pounds or pound-feet or foot-pounds squared divided by pounds, whatever you guys want to use. Not really, it's foot-pounds always. But foot-pounds squared divided by pounds is also foot-pounds. Units. Great. So we found the resultant moment, right? And I bet you if I don't know, like advance the slide one. Nope, never mind. I didn't include that one. Shoot. Or did I? Nope. All right. Well, that just puts a moment that I will draw in this nice pink color here. And it's positive, so it's what we got. It's the moment resultant at point A. And so I drew it at point A. And it's in the K direction because it's a 2D problem. It's about the K axis. Cool. All right. Now for the moment of truth here, right? We need to know part C. How far away are we? Right, so I'll keep track of MRA up here. That's going to be 509.7 K direction, foot-pounds. Okay. Get rid of this, clear some cap. I don't think we need these forces up here right now. We'll do part C. So I want to know, how far away do I have to put my resultant force such that I take care of that moment, that I produce that moment inherently, and I don't need, because really what we found was that we found a resultant, and it's just kind of, it's floating around in space somewhere, right? We want to put it a specific distance away. So how do we do it? Okay. Well, I would invite you to recall that in 2 dimensions, if we're using this scalar, the equation of a moment is the force times the perpendicular distance that force is away from the point that we are taking the moment. So what we are looking for, really, is what we're calling dA here, right? That's not great looking. Is that distance, right? Between A and where that force comes off of the bar. That's what we're looking for, okay? So in our sense, in our case here, we've got moment RA is equal to FR times dA, right? That is what the equation that we're going to be using. And if we want to solve for dA, it's the moment divided by the force, right? And if we look at the units, that would be foot-pounds divided by pounds, which would give us feet, right? So hey, that's great. We love that. Okay, so what do we do here? Well, okay, let's look at FR. FR is at an angle. We got to figure out where to put FR. How much moment produced by FR? If I broke it into just the y component, right? Because the x component goes through point A. So I really just need this 163.3. So dA is equal to the moment that we found, which was 509.7 pound-feet or foot-pounds. I accept both. Divided by 163.3 pounds. Units cancel. We're left with feet. dA is equal to 3.12 feet. And that's how we do that. And so this whole thing can be represented, right? I said, without us needing to deal with this moment at all, as long as this force is placed the distance dA away from A. So we go down from 3 forces to 1 force. That is the one, if we apply that 1 force in that spot at that angle or in those components. Great success, 1 force. Why is that important? Why is that useful? I haven't shown you why it's useful yet. We'll talk about it a little bit later today. when we start talking about reactions of things, reaction forces. But let's say that I know that that is the net force that is applied to that. By applying that, I haven't changed my external effects on my system. And I ask you to find me the reactions at point A. I want to know how much force is required for the wall to hold this. I can do this with one force, or I can do this with three forces. 6 of one, half dozen the other. I would argue that with three forces, it's not that much different than one. I would also say that when you get to something like, I don't know, maybe the space shuttle or something that has an extremely difficult truss that you want to look at, like any building that exists, you probably want to break it down to individual components, right? When you have a lot of forces on it. Some of these are somewhat trivial, but we have to start somewhere. Start simple, and then we'll move to more complex stuff. Guys have any questions about this? It is a useful tool, I promise. Are you going to use it all the time? Maybe not. But when things get really complicated and there's a lot of forces and moments acting on things, it really does help to be able to consolidate them and move them around to where you want them to be. Okay, here's a question. The forces on the pole can be reduced to a single force and a single moment at point, is it P, Q, R, S, or any? And you're going A, B, C, D, or E. The forces on the pole can be reduced to a single point force in a single moment. Where? This one's a tricky one because it's three-dimensional, guys. You can see it's X is coming out of the board, so it's tricky. Okay, we got A, C, E. E, is that a squared? Does that say E squared? It's actually secret answer F. No, it's E. It's E. Any of these points. That's the whole point of what we just did. You can take all these forces and you can, like, if you want to put it anywhere, you can. You just do that math to figure out what that looks like, right? We can put it wherever we like. Wherever we like. Boom. Black boxes are back, guys. Woo. All right. Yep. Let's do this one. This one looks super fun, right? Super fun. Is that what you would say? Probably not. Where is, please hold. I gotta find my, I gotta find this problem in my notes. There we go. Found it. Okay. This one's three-dimensional, so that seems like that ups the ante quite a bit. Also, there looks like there's some moments that are being applied here just to start with, and I don't like that. All right, the forces and couple moments are applied to this pipe. Well, also, why are we making pipes that look like this? This is, I don't know. Well, you got to bring your fluids different places. Okay, like they're going to branch. I don't know what to tell you. An equivalent resultant force and a couple moment at point O. All right, so we want a resultant force and a couple moment, and we want them specifically at point O. So we're being asked for two things: the resultant force and the resultant moment. Okay, great. Let's draw this. You guys still have it up here. There's a lot going on here. A lot going on. I'm going to try my best to draw this super accurately for you guys. Okay. So let's start here. There's my pipe. I've got here's point O. X, Z, and Y coming out over here. Just to remind myself, I will also just draw my coordinate system independently, Z, Y, and X, with the positive sense of rotation in each of my planes. Why? Because that seems like a good idea just to keep it in my mind. Okay, let's draw our forces here. This will be point C. And here's my force. It is 100 Newton. And we're calling that F3, by the way. So I will call that F3. We've got some force here at point B that we're going to call F2, and F2 is 200 Newton. But there's also a moment around here that we're going to call MC2, and I'm not going to write it there because it's going to get cluttered. We'll put our dimensions in a second. And then finally, we have point A. We have a force there. And this is F1, 300 Newton. That comes with a moment that we're going to call MC1. Ooh. All right, let's look at our dimensions here. This is 0.5 meters. A to B is 0.6 meters. B to C is 0.8 meters. This from the x-axis downward, right? That's 45 degrees. So that's nice. We can't possibly mess that one up, he says. Then he will mess it up. Okay, that's everything that's on here. That looks really complicated, right? Okay, what do we know? Well, we know F1, F2, F3, MC1, MC2, and dimensions. We have all those things, and we were asked to find two things that I'm going to label A and B, the resultant moment and the resultant force. Okay. Okay. Since we asked for the force first, let's do that thing. Let's do the force first. So part A, resultant force. Well, this one should be pretty good. As long as I define all my vectors for F1, F2, and F3, right? I should be good to go. So let's start with some of the easy ones. The F1 vector should be what? Well, that's only in the z direction, right? So it's 0i plus 0j plus 300k Newton. Great. About F2. That one's a little bit more tricky, right? That one's down at an angle off of the XY plane. So that's going to have a z component and an x component, right? And only a z component and an x component, because it's not angled. We're not given any angle in the y direction, right? So it's just angled downward. So how do we figure that one out? Well, it's going to be in the x direction, right? Let me, So it's going to be 200 times some trig function. Which trig function should I be using? It's a trick question, but it's true. It is sine 45. It doesn't matter because it's 45. You can pick whichever, you'll get the same answer, right? Is that positive x or negative x? Is it coming towards you or into the board? Towards you. Which way is positive? Towards you. If this was a 3D movie, you'd be like, no, 200 newtons, no. Okay, great, Perfect. You guys are like, what the heck is going on? It's nothing happening in the J, right? There's nothing happening in the J. This is an XZ plane force. How do I know that? Because I'm only given the one angle. That's it. I'm given the one angle, and it's just tilted downward. If it was going to be off to the side, if it was angled to one of the sides, they would have to let us know somehow. They don't. Oh, I don't know. It is cosine. Yeah. No, keep track of it for sure. Because here's the thing, something that you will often get when you get out of here is, that's great that it works at that angle. Now tell me what it is at 30 degrees. And if you pick the wrong one, then you're kind of out. So definitely don't be slackers on keeping the correct trig function in there. All right, what about z direction? What do we got? Well, it's going to be negative 200 sine of 45 degrees in the K. Does everybody see that? Is everybody comfortable with that? Yes. Okay. F3 is yep, just 100J, right? And remember, I'm just keeping track of all these things because when I add them all together, it makes it easier if I have all of them, and I'm not going to accidentally mix a J with a K or an I with a J, right? Okay, let's simplify the sine functions down, the trig functions, right? We simplify the trig functions down. Turns out that 200 times the sine of 45 is 141.4, roughly. I'm just going to write it in here so I don't have to. 141.4 I plus 0J and if I want the resultant force, this is really awesome. I just have to add these things up, right? So we'll go old school and just do that. Add the I's, add the J's, add the K's. I know they're not lined up. It's fine. 141.4 I, right? J plus 100J. This should be a negative, so hold on right here. 300 minus 141 should be 158.6. We got it. Nailed it. Resultant done. The force resultant should be the easiest part of our day, right? We just break it into components, add the components, call it a day. I'm not going to ask you for angles for 3 dimensions. This is perfectly good. Just leave it like this. Great. Now what? Well, now we got to do the moment part. Okay. If I have a moment, what, let's say this, what is the definition of a moment? Right. In 3D, what equation do we use to get the moment or something? It is in 2D. Yes, R cross F. It's R cross F. But there's a little bit more to that. Because we have moments that were applied externally, we also have to track those as part of our resultant moment, right? And so luckily, both of those happen to be positive. How do I know that? Well, because I drew my coordinate axes up there, and I saw that in the MC1 rotates about the z-axis, and that goes in the counterclockwise direction. And MC2, it's off axis, but it does it's a rotation in the counterclockwise direction. So we're going to treat it as positive for this. I'm going to clear some room here. I'm going to move my resultant force vector and then clear the rest of it. Any questions on that part on finding the resultant force? Move it up here. That's our resultant force. No, everyone's good with finding the resultant force, right? Hopefully. Okay. Let's do the next part. This is where we get some. So remember, this is asking us for the resultant moment about point O specifically, right? Should have put it here, about point O. Okay. I also want you to notice that there's no part of this question that asks us to place a single force, right, where that would take care of this moment on its own, right? And that's important to understand why. Because this is in 3 dimensions, it makes it a lot more difficult to figure out what that R is, right? Because you have to do essentially an inverse cross product, which is not something we're going to cover. We're just not. So we'll just leave the moment as is about 0.0. Okay, so let's write down our equation. If I want the resultant moment about 0.0, that's going to be the result of my couple. That's going to be the sum of my couple moments plus the sum of my moment about 0.0 from my applied forces. Okay, so there's 2 parts to this. Because we have 2 moments that already exist being applied, we just need to add those together, right? But we need to make sure that we're adding them together in a way that we need to make sure we're adding them together in a way that how do I want to say this? It's a vector, right? So we got to add, they're not just pure z direction, they're not just, they each have their own components. So we have to add the components together, right? So we're gonna have to figure out components for these, which is fine, and we'll do that in a sec. And then we add those and we'll have our MC vector, and then we have to do our cross product, the sum, right? So another way to think about this is the sum of our coupled moments plus the sum of our cross products. So we have 3 forces. We are going to have to do 3 cross products with 3 different R vectors. All right. So not super difficult. No, it's not gonna. Okay, well that meeting's starting. That's great. Appreciate that. There, perfect. Yep. And those were given to us in the problem. So if we go back to the original, right, you can see on this, you have these moments. We call them coupled moments here, but they were just, think of them as any moment that's externally applied to the system. So for some reason, this is being twisted, this pipe's being twisted, and so is this one in some way. Again, without context, it's tricky to understand, right? So all right, let's do the easy part first, and we'll write down our MCs, right? So MC1 is equal to what? Well, that's purely around the z-axis, right? Everybody can see that. Would everybody believe that, right? So if that's purely around the z-axis, we end up with 0i plus 0j plus 100k Newton meters. Okay, great. That one was easy. MC2 is not that bad. right? We just need to figure out the components of it, right? And so how do we do components? Well, we're going to need trig functions, but we know that the magnitude is 180, right? Um, this is down in the xz plane, right? So this is going to have a moment about this vector, because it's angled downward like that, and it's about the xz plane, right? Is going to have a moment in the x direction and a moment in the z direction. Okay. Nothing in the j because it's not tilted in that way. So this is where thinking of it as a rotation is counterintuitive. Think of it as a vector. It is a vector pointing downward at 45 degrees in the xz plane. We're just going to treat it like a vector, right? And when I get components of that, I end up with an I component and a k component. I will have no j component because of that. Does that make sense? It's causing a rotation, but it's still a vector. Remember that it is a vector, and so whereas vectors are concerned, you know, trig is king. So we get cosine 45 degrees in the I direction, right? So that's going to be positive, minus sine of 45 degrees in the j, right? And that whole quantity multiplied by the 180. Does everybody see where I've come up with that and where that comes from? That cool? Is everybody cool with that? Yeah, Aaron. Yeah, sorry. Thank you. Like I said, yeah, it's true. Told you guys. Told you guys. All right, so cool. So we've got sine 45 degrees in the K. Great. So there's no J component, which we just talked about. So when we do the math out, we end up with 127.3 in the I plus 0, J minus 127.3 in the K. And that's also Newton meters. Okay. Now we need to figure out the R vector. The R vectors from point O to any point of application on our forces, right? Because remember, when we're talking about doing R cross, we are talking about, we can use a vector to any point on the line of action of that force, right? It doesn't have to be to a specific place. It can be to whatever makes the most sense for us to do that, right? The other thing that's really nice, well, is that force C, right, or force 3, looks like it travels directly through point O. So we shouldn't really have a moment to that. The distance should be 0, right? Should be. Let's see. Let's see what happens. All right, so let's find R1 first. So the distance between R and force 1. I'm going to draw it up here so we can see it. This distance right here. This is R1, right? Remember, it's to any point on that line of action, and that crosses at point A. So it's really R from O to A, which is just what? It's 0I plus 0.5 J plus 0 K, right? Cool. Does that make sense? Everybody cool with that? Okay. I'm going to draw this one, and I'm going to draw it next to it because I don't want, well, I'll draw it from the end of R1, but just assume that R1 sits on top of it, okay? Because I don't want to overwrite R1. Anyway, if I start at O, I'm going to claim that this is R2. And you're going to say, but Dr. D, what about that 45-degree angle? That makes me feel really uncomfortable, and I don't want to deal with that. And I'm going to tell you the same thing I said a moment ago. It is the vector from point O to any point along the line of action of that force. And it turns out that if you draw the line of action of that force, it ends up back on the bar. So we just need the J distance, and the other ones are zero. I don't want to deal with that 45-degree angle either. How am I supposed to know that that's not something I should deal with? Okay. Context of this problem. Are you given any information about what distance, what drop you have there? No. You're not told how long that pipe is. You cannot. There's no way for you to figure out any of the X or Z distances there. Period. Right? But remember, I told you guys the other day, it is 100% true because this is an academic exercise, is 100% true that you can solve any problem given all the information that you're given, right? It has to be true. Otherwise, this whole thing breaks down. And that doesn't hold true for like capstone and stuff like that, where you're working on real world problems. But in this class, where it comes out of a textbook, there's definitely an answer, right? And it has to be able to be gotten through the information that you're given. Okay. And then finally, R3. What's R3? It's 0. Why is it 0? Because it passes through point O. The line of action of that 100 Newton force goes right through the origin, which is right where we're trying to take the moment. So there is no distance. There's no distance between point O. So we're not even going to deal with it. We're just going to deal with the 2. Right? We've already added our applied moments. Now we need to do our cross products for this, right? So I'm going to clear some space up here. Is everybody cool with what we've done so far? Everybody good? Any questions as of right now? Yeah. Yep. Because the distance, so we can write the vector R3 from here to here, right? But what you're going to find is if I can move this, I can move any force along its line of action, right? So if I take this force and I move it all the way back here, maybe, if it lets me, right? I move this back here, it's at point O. So the distance is 0. If you were to write it out as 1.9 in the J, because you can, what you're going to find out is when you go to take that cross product, the cross product is going to be 0 anyway. All right, because you'll end up with 0, 1.9J, and 0, and you'll end up with a force that's 0, 100 in the J, and 0. And so when you cover up all those things, you have zeros canceling all the way across. So the math will prove it out anyway. But if we use a little bit of what we know about vectors and moments, we save ourselves a few minutes of having to take that cross product. Which, you know, maybe you can use that time to get your dailies done or whatever. Hop on your Fortnite, do whatever it is kids do. Roblox. Hop on your Roblox. No? Nobody? All right. Just me? That's cool. All right. So I've got these things. Now I got to find, right? So if I want let's call them moment 1. Well, that's confusing. Let's just write the whole thing out, right? So I've got, I want my R cross Fs just for our edification. We're going after that right now, right? So the first one is going to be R1 cross F1, right? We have all of that. So I, J, K. R1 is 0.50. F1 we found earlier as 00300. if we do this cross product, right, we go through the whole thing, we get, well, 100, 150 in the I, right? Does everybody see that? If I cover the I column, I get 0.5 times 300 minus 0 times 0. Everything else is 0. So there we go. Nailed it. If I do R2 cross F2, this one's a little bit more complex. Put my circle up here just for funsies. 0, 1.10. My force F2 was 141.4. 0, negative 141.4. Right. This one's going to have two components. We can't get away from it, right? If I cover up the I get 1.1 times negative 141.4 minus 0, right? So that should give me negative 155.4 in the I. If I cover up the J column, I get 0 times negative 141.4 minus 141.4 times 0, so no J component. That should make sense because we're not twisting. We can see clearly that that force does not angle in the J, right, at all. And K, 0 minus 141.4 times 1.1, which is again a negative 155.4 in the K. We just add all of those up. We add the MCs up. We just add all the components up, right? So what do we end up with, right? Well, we found that MC2 had 127.3 in the I, right? So here, let me just write the whole moment equation out. MR vector is going to equal 127.3 I plus 0 J minus 127.3 K plus 100 K, right? So that's MC2 and MC1 that I just put together, plus 150 I minus 155.4 I minus 155.4 K. And so we will simplify this, right? We'll do the math. And when we do the math, we get 121.9 I minus 182.7 K Newton meters. Okay. The hard part of this is creating the moments, and that's more conceptually hard than mathematically hard, right? This is mostly understanding where the vectors are and what vectors I need, right? So it looks scary to start with, for sure, right? There's a bunch of stuff happening. It's three-dimensional. It's crazy. But we can break it down and keep it relatively simple, right? You guys have any questions on this one? No, nothing? You guys good? Okay. It's crowded. It's gross looking. It's not that bad. Not that bad. Right? Remember, these are at point O. The force is at point O and the moment's at point O. Okay? So we would draw our resultant force at point O, and we would draw our moment at point O. What would that look like? You would, I would draw the components individually as vectors and call it a day. We weren't asked to draw it, so good for us. We're done. Okay. Questions? Any other questions before we launch into the next thing? Put it back up. Anything? Anything about this? Not anything. And specifically about the problem we just did. Alrighty. Well then, let's talk about distributed loads, right? So why do we even care? Why do we even care? Well, we're gonna find out why we care, but let me ask you this, just based on what we're doing here. The resultant force Fr due to the distributed load is equivalent to the blank under the distributed loading curve. W is a function of X. So if I wanted to create a single resultant force from this curve, what do you guys think? Is it based off of the centroid under the curve, the arc length under the curve, the area under the curve, or the volume under the curve? What do we think? Jaden, that's so definitive. Man. I appreciate the punctuation for sure. Looks like we've got a bunch of C's, a couple D's. Answer is C. It is the area under the curve, which is great because that indicates what? What is area? Area is what kind of property? How many dimensions do we need to find the area of something? 2. That's awesome. Okay. All right, the line of action of a distributed load's equivalent force passes through the blank of the distributed load. Centroid, midpoint, left edge, right edge. I was thinking about when I almost fell down. That was funny. It's funny now. All right. Got some B's, got some A's. All right. It's A. It's the centroid. Now you're probably like, well, Dr. D, what's the difference between the centroid and the midpoint? It's a great question, right? Sometimes they're the same. Sometimes they're not. All right. Centroid is, think of it as, I don't want to call it the center of mass. Sometimes it lines up with the center of mass, sometimes it doesn't. But think of it as where you're concentrating all of the geometry of the shape, right? Think of it that way. And we'll talk more about it in a minute. Okay. Why do we care? Okay, so say I got to stack this plywood. We're going to call it a bunk because apparently, and as I learned, that is what this is called. A group of plywood is called a bunk. This is a bunk of plywood. Amazing, right? So, bunk. All right, it's 2x4s, right? It's stored on the storage rack. The lumber places a distributed load due to the weight of the wood on the beams holding the bunk. Okay, so this isn't a point load, right? It's not just one point of contact. There is a whole loading distributed across from A to B, right? Okay, and it's pretty uniform. You can't really see it. These blue lines here indicate that that's a rectangular distributed load. Okay, great. What else do we normally, what other quantities? Let me ask you this. It's an impolite question, but how much do you weigh? How much do you weigh? You don't have to answer it. Okay, great. Where is that located? Is that a point force? No, that's your distributed load. But we all will tell you that that acts from the center of gravity of your body, which, I mean, if you were to cut off like your leg, that's going to change your center of gravity, right? But that leg still has weight. Anyway, to analyze a load's effect on a steel beam, it is often helpful to reduce a distributed load to a single force. And how are we going to do that? Well, it ties into that question we just asked you. What's the area under the curve? And if you forget that, this distribution is typically given in like Newton per meter or Newton per meter squared, right? And so like if I multiplied by the area, I would get back to newtons, right? All right. Here, I've got wind blowing on this sign. It's a triangle sign, and it says that it's brown, but I don't believe that that's brown, but that's fine. Maybe it is. All right. I've got uniform wind pressure acting on this sign. If I want to be able to figure out what the net effect of that wind pressure is on the signpost, I should probably, it's a lot easier for me to condense that into a single point loading. And this is why we were so concerned about, can we move these vectors around to wherever we want them? How do I consolidate and simplify these force systems? Because being able to consolidate them here is really helpful, okay? Another one, right? So if you look at this, the units of our distribution are force per length, okay? So think about it if it's a rectangle. What's the area of a rectangle? The length times the width. If the length is in meters and the width or the height is in Newton per meter, when I multiply those things together, I get newtons, right? It all comes down to a units problem at the end of this. So if you don't remember that this is supposed to be the area under the curve, the units should help you when you look at the distribution. Like, how do I isolate the force? Well, I need to multiply by the distance. Okay. Now, a lot of these, well, all right. So yeah, we can go through this. We just kind of talked about this. You have to find the center, not the center. You have to find the centroid of the shape, and that's where it's acting, right? And so you'll see this notation quite a bit. They call it X bar in the book. So I can reduce all of this down to a single force acting some distance X bar away from some point, in this case, point O. Okay, great. We're not going to go through the whole derivation, right? The point of the fact of the matter is that the net force is the area under the curve. The nice part about this is that for most geometries, those areas are known. There are known formulas for them. You can, and we'll talk about later in the class when we talk about moments of inertia, how you can calculate all of the centroids yourself using double integrals and things of that nature. But for right now, area under the curve. How do you find the magnitude? Well, now that we know the magnitude, how do we find the position? You take the moment. It's what we just did before, right? I found this magnitude resultant force. It's going to create some moment when I condense it. What is that distance away that I need to put it so that we don't have to write the moment on there? Same deal, right? Great. But where is X bar? It's there. It's easy. Just do that. Just do those integrals. It'll be fine, right? We'll talk about it in more detail later. But for right now, point C is what we call the geometric center or the centroid of an area under a loading curve, right? So point C, that's we're looking for the centroid. Sometimes you'll see it drawn as a circle with an X in it and it's colored on the diagonal, right? It's fine. Don't worry so much. Like you can do this. You can find the integral of x dA and the divided by the integral of dA all with along the area, right? Along the shape of the curve. We can do that. But until we get to that point, we're going to consider mostly rectangular and triangular loadings. I say mostly. This says only. It's going to be mostly. Okay, mostly. There's tables in your textbook that give you all of the locations of the centroids for all of the things, right? And in practice, you would never memorize any of these, right? You're just going to go and you're going to look up, okay, there it is, go. Again, some of them you will use so often, like rectangles and triangles, that you just know it. And it's burned into your brain forever. And when scientists look at your brain after you pass, they will see the secrets of distributed loadings in there. Great. Now, let's complete the calculations to find the concentrated loads. Great. So I've got these two concentrated loadings here. Okay. Perfect. I've got this rectangular distributed load that has a distribution of 400 pound per foot. And part B is this triangular one that has 600 Newton per meter applied over 6 meters. Before we get into any, so notice this says 100 x Newton per meter. Okay, so this is the slope of this line is 100 Newton per meter, or 100 Newton per every meter, right? That makes sense? Yeah. Normally when you're given the triangles, we don't really care about this. We're just looking for this number. You're going to be given the maximum magnitude of that triangle. What is the maximum magnitude? But if I were to cut this beam here and it was 1 meter long, top of that triangle is only 100 meters or 100 Newton per meter, right? All right, so let's start with this, right? We want to calculate, we want to figure out where this thing is, right? And you guys can, if you want to look at your textbooks, you can, but we're going to start with the rectangular one. And I'll draw a little diagram here. What do we know so far about this? We know a couple of things. The magnitude of FR for rectangle or resultant. The resultant for this, right, it's not a vector, it's just the magnitude, is what? Well, you said it was the area under the curve. Because it did say that, because that's what it is. So how do we do that? Well, that's a rectangle. That's going to be 10 feet times 400 pound per foot, right? The length times the width. And so we should get, carry that, 4,000 pounds. Area under the curve. Great. Is it that easy? It can't possibly be that easy. You were just talking to us about doing cross products and moving moments to God knows where. And yes, it is that easy. This is how it goes. It's the area under the curve. You know what the curve shape is. You find the area. Great. Where does that go? Goes at the centroid of the shape. What's the centroid of a rectangle? It's the middle. It's the middle. FR 5 feet. Mic drop. Done. Mind blown. Cue all the GIFs, the memes. Okay. You guys know what I'm talking about. Exactly. All right. Great. That one's super easy. Rectangle, no problem. What about this triangular one, which we'll do in this nice purple color? Okay. What is the area under the curve for the triangle? Well, for a triangle, the area under that curve would be 1/2 of the base times the height. Maybe. Yeah, there we go. So what's the base here? Oh, 6 meters. What's the height? 600 Newton per meter. So 1,800 Newton. Half of 6 is 3. 3 times 600, 1,800. Nailed it. Where does this go? At the centroid of the triangle. Where's the centroid of the triangle? Yeah, it's 2/3 from the small side or 1/3 from the fat side, right? So think about this. What is this saying? What is the centroid actually telling us? It is telling us the center of the area, right? In a rectangle, it makes sense that it would be dead center in the rectangle because of the way that we calculate area, right? It's an even distribution of area. The triangle has much more on one side than the other, so that's going to skew where our centroid is. And turns out for a triangle, that pushes it to 2/3 from the skinny end, which would be 2/3, 4 meters from the skinny end, or 2 meters from the other side. Which side you want to calculate it from depends on what the question is asking you and all of those things, but that's generally how it goes. So pretty straightforward, right? Not too bad. We can all do that. So, questions about how to locate rectangles and triangles. What if I don't have a rectangle or a triangle? Well, then you look it up in the back of your textbook where it told you to look it up. There's also this thing, it's called Google, that not a lot of people are using, that you can ask for that sort of information. And Dr. Chad GPT probably knows the answer too, but sometimes he makes stuff up because he wants to be relevant. Okay. Okay. Oh, what the heck? Loading on this beam is given to us. What are we supposed to do with this? Equivalent, well, I want the equivalent force and its location from point A. Well, boy, howdy. This is not a triangle and it is not a rectangle. It is both a triangle and a rectangle. We will split it into two shapes. It's crazy. So let's give it a go. Okay. So this takes into account all the things that we were just doing with simplifying force systems, right? So if I draw my really expert free body diagram here, where this is point A and this is point B, let's start with the triangle. Okay. With the triangle, I've got this, right, and this is going to be 6 feet. And then I'll draw my just for completeness. And that's 8 feet, right, from here to here. Oh. There's 8 feet from here to here. Okay. So I want to start here. I know, like we just did this, right? I'm going to call that F1, and we're going to call this other guy here F2. Now that's crowded to look at, I agree, but I'm doing this on purpose just to show, right? So we need to find the magnitude and the position of F1 and F2, right? We already know the position, kind of, right? Because we know that it's a triangle, so it would be 2/3 across from A, and we know that F2 has to be the center of that rectangle, right? Let's get the magnitudes first. So F1 should equal 1/2 of the base, which is 6 feet, times 150 pounds per foot, right? Which should give us 450 pounds. The distance to point 1 from A, right, is going to be 4 feet because it's 2/3 of the way from A, right? So is everybody tracking with me? I know this is going pretty quick compared to other stuff, but is everybody cool? We cool so far? Yeah? This means that we're left with 2 feet here. And you're like, that, I know that. You don't need to tell me that. And it's not for me to tell you that. It's because later we're going to need that 2 feet. And I don't want you to forget about that 2 feet because the 2 feet is going to be pretty important. F2. Well, that's going to be 8 times 150, which gives us 1,200 pounds. And the distance to point 2 is going to be 4 feet from there. But we're concerned with it from point A, right? So it's 10 feet. Why are we concerned with it from point A? Because we were asked to find the equivalent force and location away from point A, right? That's what we were asked for. So we need to create a resultant force. How do we do that? Well, we're going to add these two forces. They're both in the J direction. Makes sense. We just add them. Great. How do we find the distance it is away? That one will. So what happens, right? We did this earlier, right? What happens when we have two that we then create a new resultant force from, right? So we started with a distribution of force and I consolidated them, right? So net effect of both is still preserved. But then if I create another resultant from those two forces, what happens? The distance changes, but why? So I didn't just create a force, right? Because that so remember what I did right now is if I do all of this, then F is applied, the new resultant is applied at point A. If the new resultant's applied at point A, what part is not being accounted for anymore? There's some other stuff that we need to take into account. Yeah, there's a net moment that also gets created by moving to point A to counteract the effect of moving the force. So we're going to need to figure out what that moment is, because what we want to do is we want to move that force, the new resultant force, out so that we don't have to worry about what that moment is, so that it establishes that net effect. So first things first, let's find the resultant. Simple, F1 plus F2. 1650. About 1650. Sorry, 1650. Okay, great. What about the moment at A? Well, the moment at A is going to be the moment generated by F1 plus the moment generated by F2. Okay, so what's the moment due to F1? Well, this is a 2D problem, so this should be F1 times D1. Is that going to be positive or negative? Yep. And the moment due to F2, which would be F2 times D2, was that positive or negative? Also negative. Great. Great and good. So we plug in our stuff. We've got F1 is 450 times 4 minus, and that's negative, minus 1200 times 10. So this gives us a net moment of negative 13,800. That's a lot. I don't know, maybe it's not. Depends on the application. I mean, it looks like a beam or a bridge type deal. So should probably be able to hold a lot. 13. Anyway, I mean, the forces were 450 and 1,200 pounds. So, I mean, this is decent, I guess. Anyway, so now we have that. So what do we have to do? Well, let's do it this way. MA is equal to our resultant force times the distance that it has to be away from point A, right? Because remember what we did, the intermediate step that I didn't draw is that resultant force is at point A. Because of that resultant force, we have a moment about point A. I can account for that moment by moving that force from A, some distance x bar away from A, right? And so I'm doing this guy, so I need to divide my moment by my resultant force, right? So x bar is equal to my moment at A divided by the resultant force. So x bar is equal to negative 13,800 divided by negative 1650. Why are both of those negative? It's because the force is pointed downward and I didn't account for that because it was a scalar up there. It's fine. If you get a negative distance, please investigate that. You can see very clearly that there is no beam. Like if you get a negative distance and you have something in the middle, okay, right? That makes sense. Point A is the furthest point. That's like saying, all right, I've run my experiment and we're going to start at time 0, but I want to tell you about what happened at t minus 100 seconds. You didn't start recording data until t equals 0, right? You can't do anything that's not on the beam, right? When you do this, you end up with 8.36 feet, okay, which is somewhere in between the 4 feet and the 10 feet. Physically, does this make sense? I would argue yes. You have more distributed load coming from the rectangle than you do from the triangle. So that's going to make it push more out towards the center of the rectangle, right? That's just what's going to happen. All right. So complex shapes, you can break them down into simpler shapes and do this, right? And this allows us to simplify our systems, and it's great. And it's the same stuff we were just doing, but it seems a lot simpler, right? Because it's in 2D and not that bad. Okay. Questions about this? Again, this is a little bit out of context also, I will say, right? And the reason that I'm saying that is specifically because this is great that we can do this, but I haven't talked about why we would want to do this. And why we want to do this is something that we're going to start talking about probably a little bit more now, well, definitely a little bit more next week, okay? It has to do with, again, because I have this loading on this beam, can I determine what my reaction forces are? Are the things that are holding this in place strong enough to actually hold it in place, right? That's the design side of it. What we're going to get is, yes, I can calculate the reaction force, right? There's not a ton of context beyond that in this class. Yeah, let's see. Here they are. And then 8.36 feet right there. Teed it up. Okay. What is the location of FR here? What's the distance D? I know it says distanced. There's supposed to be a space. 5 meters? Yeah, 5 meters. Why is it 5 meters? Well, it's 2/3 away from the skinny end plus 3 meters, right? Okay. Now this one, if F1 is 1 Newton, X1 is 1 meter, F2 is 2 newtons, and X2 is 2 meters, what is the location of the resultant? Well, we've got to calculate moments to do that, right? Just like we just did. So we would take the moment of F1 plus the moment of F2 times their distances, right? And then solve for X bar with our resultant. Turns out this is 1.67 meters, which don't worry so much about that. That's fine. Let's try this one. What's the resultant force? You guys calculate it. Put it on the boards. On the boards. Probably somebody is really excited that class is about to end. So interesting choice to create a 13-minute alarm. Yeah. All right. What we got? What we got? Hold them up. All right. In the back. Let's go. This is 100. Okay. We got I got some 400s. I got mostly 600s. It's 600. Why is it 600? Half of the base times the height. One half of the base times the height. Where is this located? That's the next question. Where is this located? Uh, Make sure to include units, please. Place. Okay. We got answer is 4 meters. 4 meters. It is 1/3 from the fat end. That was a tricky one because all the other ones we did were 2/3 from the skinny end. It still is 2/3 from the skinny end. It's just reported from the fat end. Ooh. Savage. All right. I'm going to introduce topic 4, then we're going to call it a day, probably in a second. I've got 10 more minutes and we're going to use them. All right. Topic 4. This is the second topic for the next quiz, right? 3 and 4 are quiz 2. This is analysis of trusses, frames, and machines. This is where we're going to hit some actual statics, as it were, as they would say, right? So we want to be able to develop equations of equilibrium for rigid body, create free body diagrams for rigid bodies, apply equilibrium analysis to rigid bodies, determine the force in the members of a truss, and analyze the forces acting on members of pin-connected frames and machines. All right. So conditions for rigid body equilibrium. Okay, this is a beam. The beam and the cable, and we're going to say that we have frictionless pulleys that are also massless, and it supports an 80 kilogram load at sea. Here is the question. How does this beam stay up? It's obviously changes in density, like we talked about earlier in the week, right? But for serious, how is this staying up? What is causing this to stay in that position? A reactionary force, sure, sure, right? This 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 pulley up here has to be doing something. It's not free floating, right? And what Colin said is right, right? There's a reaction here holding the pulley in place. We call them reactions. We call them reactions. Reactions prevent motion. Okay? They do. That's what they do. That's what I want you to think about when we talk about reaction forces. Okay? It's not an actual force that's, let me say, be careful on how I say this. It is how the environment is reacting to your object, your system, to create static equilibrium, which is why we call it a reaction. Okay? So how does this beam prevent rotation, right? What sorts of reactions would we expect here, right? And this is a problem we did the other class. I think it was on Tuesday, maybe. We simplified this couple system, right? And this is going to cause a moment, right? This is going to cause a moment on this beam. So what keeps it in place? Well, there has to be a counter moment from the wall that holds it in place. And this is what we were talking about, right? When I bring it back to the context, when you're sitting in the chair and it almost tips over, right? You've created too much moment. It wasn't enough support there. There wasn't enough reactions, right? This needs to be able to counteract the moments and the forces that are acting on this beam so that it doesn't rip out of the wall. So here's the big picture, right? Or a big picture. It's a regular size picture. Truck ramps have a weight of 400 pounds each, right? So here's a truck ramp. Each ramp is pinned to the body of the truck and held in position by a cable. So what's the difference between these two free body diagrams? What is it? It's true. This one's not a free body diagram because there's no forces on it at all. But if there were, what it's trying to show you is that the tension and the reactions at A are both reaction forces. So there's a difference between how we would solve this and how we would solve this, right? If you look at this, I've got 1, 2. I should probably know. I know what the weight of the truck ramp is. I was just told, right? 1, 2, 3 unknowns. Probably have 3 equations that I can use to determine those, right? What does the F in free body diagram stand for? It stands for free. This means that we need to remove it from its supports. If we remove it from its supports, then what do we have to account for? All of the reaction forces that are holding it in place due to the supports. Okay? So you will never draw pins or rollers or any other types of supports in this class. You will only draw the forces that, or the moments that they exert on the body that we are interested in the system that we're interested in analyzing. Great. So in this case, I've got 2 smooth pipes. I mean, it's relative. Each having a mass of 300 kilograms, and they're supported by the tines of the fork, the loader's fork attachment. So if we determine we want to determine all the reaction forces, what do we have? Well, we've got some force here pushing up off of the base of the tines that they've called T, and we've got these normal forces from here, right? And those, when we remove this, these forces come into play. Why? Because you have to pretend you took away what is supporting them, right? But those are typically the quantities that we are interested in. We want to know specifically, is this forklift going to be able to support the load that we have put on it, right? And in order to know that, and we'll talk more about bending and all that stuff, right? So how do we make use of an idealized model and a free body diagram? Well, we'll find out, right? But conditions for particle versus rigid body, right? We talked a little bit about this at the beginning of class. Here's a particle, here's a rigid body. Notice, everything passes through the center here. Not everything passes through the center here, right? So for a rigid body to be in equilibrium, the net force as well as the net moment about any arbitrary point, which we're going to call O, must be equal to 0. So this is the great thing, is that you can take the moment wherever you like. It doesn't matter. You can do it wherever you want, any point O. Some points are better than others. We'll talk a little bit more about that as we get closer, right, to probably next week. But sum of the forces equals 0. That one makes sense, right? So what do we have to do? We start with our actual physical system and we create an idealized model. So assume negligible friction, assume that we have weightless, massless, frictionless pulleys, no wind resistance, all that stuff, right? And then we draw a free body diagram showing all of our external active and reactive forces. So, every force that is acting on there, and then we apply our equations of equilibrium, right? Sum of forces in the x and y direction, sum of the moment. Doesn't matter which ones. This is a fun fact. You can actually take 3 moment equations, and you don't even need to use sum of the forces if you don't want to. I don't necessarily recommend that all the time, but there are certain instances where that might be helpful. It's fun. Okay. All right. Hang tight. Probably just start with this for the next time. Yeah, we got 2 minutes left. I'm not going to rush through free body diagrams, but we'll talk about FBDs. We'll talk about the different types of supports next class. That would be on Monday. And and here you guys go. We got our customary Friday poll everywhere. How is everybody feeling about class so far? We're at the end of week 2. Please don't forget to do your homework. Please don't forget to do your project plan, right? Please don't forget those.
About the water tower plan.
Mhm.
I was looking for market like yesterday. And I was wondering if you wanted like just a random village